In the real world of production, a successful AI feature can be your greatest liability. Imagine a startup launching a high-end coding assistant. They charge $20 a month, but a power user generating thousands of lines of code can easily consume $30 in API tokens from providers like OpenAI or Anthropic. This is what I call the success tax. The more your users love your product, the more money you lose. I have seen teams forced to throttle their best users or disable high-context features just to keep the lights on. It is an architectural dead end where your margins are at the mercy of third-party token pricing and constant network latency. We are building on a foundation of shifting sand where the infrastructure costs grow linearly with your user base, creating a ceiling for your business growth. We need a fundamental shift in how we think about the compute debt of modern LLMs. But what if the cost of inference wasn't your problem at all? By the end of this lecture, you will see how to flip this script entirely. The alternative is a paradigm shift, browser-based inference. Instead of your server farm burning through GPU hours to predict the next word, we utilize the user's local hardware, their M-series MacBook, their RTX-powered gaming rig, or even high-end mobile devices. By moving the model to the client side, your token cost drops to exactly zero. You are essentially crowdsourcing the compute power of your entire user base. Beyond the financial reversal, you gain two massive technical advantages: zero latency interaction since data never leaves the device, and a level of privacy that is impossible to guarantee with server-side logging. We are moving from a centralized pay-per-word model to a distributed bring-your-own GPU model. This allows for features that were previously too expensive, like real-time text analysis or local first RAG. But is this just a theoretical pipe dream for 2026? Let's look at why the browser environment is finally ready for the big leagues. For years, AI in the browser was a slow, experimental toy. WebGL was never designed for general-purpose GPU computing, and WebAssembly lacked the SIMD instructions required for heavy tensor math. However, the year 2026 marks the absolute maturity of WebGPU as a global standard. It is no longer behind experimental flags in Chrome. It is fully shipped and optimized in Safari 19 and Firefox 140. We have moved from simulating hardware to having a direct, low-overhead pipeline to the GPU silicon. This standardization means that a single codebase can now target the metal of almost any modern desktop or mobile device. We are seeing the death of Works on my machine for AI, replaced by Works in your browser. The technical barriers have crumbled, and the browser has become the most widely distributed AI runtime in human history. But talking to the hardware is only half the battle. The real question is how fast it actually runs. Is it enough to compete with native applications? The promise of this lecture series is what I call the 80% threshold. Through modern optimizations like 4-bit quantization and specialized shaders in WebLLM and Transformers, we can now reach roughly 80% of the raw performance of native QDA or Metal applications right inside a single browser tab. Think about the implications. You don't need a 5 GB Python environment, you don't need complex Docker setups, and your users don't need to install anything. You simply deliver a script tag, and the browser handles the rest. We are achieving near-native speeds for models like Llama 3 and Mistral while bypassing the entire DevOps headache of scaling a GPU cluster. This course will teach you how to bridge that final gap between it runs and it's production ready. We are going to look at how to manage model loading, memory constraints, and the UX of heavy local compute. To master this, you first need to meet the core trio of engines that make this magic possible: WebLLM, LiteRT.js, and Transformers.js. When we talk about high-performance local inference, we have to start with WebLLM. In the field, many developers think putting an AI in a browser is just about running some JavaScript. That is a massive misconception. WebLLM is built on the MLC LLM framework, which doesn't just run models. It compiles them specifically for the web GPU hardware backend. This isn't just a wrapper. It's a bridge between raw GPU shaders and your application logic. While WebGPU provides the massive parallel compute needed for tokens, WebLLM also includes a WASM fallback. But let's be honest, if you are falling back to WASM for a 7D model, your user experience is already dead. The real power lies in the direct hardware access that allows local LLMs to rival cloud latency. But having the power is one thing. Making it easy for your existing team to use is another. Do we have to rewrite our entire codebase just to switch from the cloud to the browser? Teaser: the answer lies in a surprisingly simple interface that mimics the giants of the industry. The biggest friction point in tech adoption is rewriting code. The maintainers of WebLLM knew this, so they designed their API to be almost identical to the OpenAI SDK. In real-world projects, I've seen teams migrate from expensive GPT-4 API calls to local Llama 3 models in less than an hour of refactoring. You simply swap the base URL and the client initialization. Instead of hitting a remote endpoint, the chat completion call triggers a local worker thread that talks directly to your GPU. This OpenAI compatibility isn't just convenience. It's a strategic move that allows for hybrid architectures where you use cloud AI for complex reasoning and local AI for fast, private drafting. However, don't get too comfortable with the code parity. Question: just because the code looks the same, does it mean the hardware can handle it? This is where we hit the cold, hard wall of browser memory limits. In the field, "it works on my machine" is the most dangerous phrase. A standard 7B parameter model takes up about 14 GB of VRAM in FP16 precision. Your user's browser will crash instantly if you try to load that. This is where 4-bit quantization becomes the hero of the story. WebLLM uses highly optimized 4-bit weights that shrink a massive model down to roughly 4 or 5 GB. It's the difference between an out-of-memory error and a working product. We use a process called weight-only quantization, where the math is still done in higher precision, but the storage is compressed. This allows models to fit into the shared memory space of modern integrated GPUs found in MacBooks and Windows laptops. But remember, quantization isn't free. You trade a bit of intelligence for a lot of accessibility. Payoff now that we've mastered text. You might wonder about vision and audio. For those, we need a different set of specialized tools from the giants at Google and Hugging Face. While WebLLM dominates the text space, Google's LiteRT.js is the evolution of TensorFlow. Lite is the undisputed king of specialized edge AI tasks. If your app needs real-time hand tracking, background removal, or audio noise suppression, an LLM is the wrong tool. In practical engineering, you want the smallest model that solves the specific problem. LiteRT.js 2026 builds on the MediaPipe heritage, offering a 3x speed boost over previous versions by utilizing dedicated NPU paths in modern silicon. I've seen developers try to force a multimodal LLM to describe an image, when a 5MB LiteRT vision model could do it in 10 milliseconds with zero latency. It's about choosing the right weapon for the right battle. LiteRT is your surgical scalpel for vision and audio. Question, but what if you need the massive library of Hugging Face models? Can we get that same native speed for the millions of models on the hub? Transformers.js has always been the gold standard for ease of use, but version 4 is a complete architectural overhaul. For years, we dealt with the overhead of running complex logic in pure JavaScript. By 2026, the core runtime has been rewritten in C++, compiled to WebLLM with SEMD and multi-threading enabled by default. This change is massive. It means the same ONNX models that run on servers can now run in your browser with near-native performance. Whether it's BART for embeddings, Whisper for transcription, or specialized Flux-style image generation, Transformers v4 acts as the universal adapter. In the field, we use this for multimodal pipelines where we transcribe audio with Whisper and then pass the text to Llama. All happening locally, all in the browser. Payoff, we now have 3 incredible tools, but using them all at once is a recipe for a crashed browser tab. You need a decision matrix. Choosing your stack isn't about which library is better, it's about which constraint you can live with. If your primary goal is a chatbot or a text-heavy assistant, WebLLM is your only choice because of its deep optimization for large KV caches and 4-bit LLM kernels. If you are building a creative tool for image editing or a real-time translator, LiteRT.js will give you per second that users demand. For everything in between, especially when you need to leverage the vast ecosystem of Hugging Face, Transformers.js is the bridge. In my experience, the most successful 2026 browser AI apps use a multi-engine strategy. They use LiteRT for detecting user intent via voice, and WebLLM for generating the response. This decision matrix I'm showing you is the result of hundreds of failed deployments. Use it to skip the trial and error phase. Teaser, but even the best library can't save you if you don't understand how the pixels actually get from the GPU to the screen. That's why in the next chapter, we're going under the hood to see the GPU to screen pipeline. In the field, many developers think that simply calling a library like WebLLM magically makes things fast. But let's look at the reality. When you execute an inference task, your JavaScript isn't actually doing the heavy lifting. It's the compute shaders written in WGSL, the web GPU shading language, that are the real heroes. Every single matrix multiplication in a transformer model is decomposed into thousands of parallel threads running on your GPU. The browser takes your high-level commands and compiles them into a pipeline state object. I've seen countless projects fail because they didn't understand that web GPU isn't just faster JavaScript. It's a completely different paradigm where you manage resources like bind groups and pipeline layouts manually. If you don't optimize your WGSL code for the specific memory alignment of the GPU, you'll see a massive performance drop regardless of how powerful the hardware is. Understanding this low-level translation is the first step to moving beyond being a library user to becoming a real performance engineer. But wait, even the fastest shader is useless if the data is stuck in the wrong place. The biggest performance killer in browser-based AI isn't the calculation itself, it's the data transfer bottleneck. In a standard server-side setup, you have high-speed NVLink or PCI lanes. In the browser, you're operating inside a high-security sandbox. Every time you move weights from the CPU memory to the GPU VRAM, there's a cost. Real-world experience shows that if you're constantly uploading and downloading buffers for every single inference step, your frame rate will tank. We use staging buffers as an intermediary to map memory between the host and the device. You need to minimize these transfers by keeping as much state as possible, like the KV cache for LLMs directly in the VRAM. I often see juniors trying to read back the results to the CPU for every token, which is a disaster for latency. You must learn to orchestrate your data flow so the GPU stays busy and the bus stays clear. But even if your data flow is perfect, a single mistake on the main thread can freeze your entire UI. This brings us to the necessity of true concurrency. If you run your inference on the main thread, your users will hate you. The browser's UI thread is for interaction, not for crunching billions of parameters. This is where web workers and shared array buffer come into play. In professional-grade browser AI, we move the entire web GPU logic into a dedicated worker. By using shared array buffer, we can share memory between the main thread and the worker without the expensive overhead of structured cloning. However, remember the Spectre vulnerability. This means you need specific SOAP and COAP headers on your server to even enable these features. It's a common pitfall. You write perfect code, but it fails in production because your infrastructure isn't configured for high-performance cross-origin isolation. You need to design your architecture so that the main thread only handles the UI state while the worker manages the inference loop. This separation of concerns is what distinguishes a hobbyist project from a production-ready application. So now that we've optimized the execution, how do we handle the massive 2GB model file that needs to be loaded every time the user refreshes? Downloading a 2GB model every time a user visits your site is a non-starter. You'll burn through your CDN budget and kill the user experience. In the field, we solve this using IndexedDB and the Cache API. While local storage is too small, IndexedDB can store several gigabytes of binary large objects, BLOBs, efficiently. The strategy is simple. Check if the model version exists in IndexedDB. If not, fetch it once and store it. However, the Cache API is often better for model chunks because it integrates directly with the browser's fetch mechanism. I've seen teams struggle with storage limits. Remember that browsers can evict your data if the disk runs low. You need a robust catch-then network strategy and a way to verify the integrity of the stored weights using SHA-256 hashes. If your model file is corrupted during storage, your inference will output gibberish, and you'll spend days debugging the wrong thing. But is just storing the file enough? Let's look at how we actually load these massive files without making the user wait forever. In practice, we don't just download one giant file. We use dynamic loading and chunking. Libraries like Transformers.js and WebLLM allow us to load models in parts. By utilizing the Hugging Face Hub's infrastructure, we can pull only the necessary shards of a model. This is critical for progressive loading indicators. Instead of a generic loading spinner, you can show the user exactly which layer of the model is being initialized. For example, in a React or Vue app, you'd use a progress callback from the library to update a state variable. Look at this code snippet. We're not just calling load, we're monitoring the stream. This allows the application to become interactive just in time. Also, pay attention to the quantization format. Loading a 4-bit quantized model, QFF16, is significantly faster than a full 16-bit one, with minimal loss in accuracy for most tasks. This is the difference between a 10-second wait and a 40-second wait. But what happens when the hardware itself says no? The most common failure in production isn't a bug, it's hardware exhaustion. Your user might be on a cheap laptop with an integrated GPU that only has 52 MB of shared VRAM. If you try to load a 2GB model, the browser tab will crash, or worse, the entire OS will freeze. You must check Navigator.gpu request adapter limits before you even start downloading. This is your reality check. If the VRAM is insufficient, you need a fallback. The best practice is a tiered approach, WebGPU for performance, WASM with Cyan as a second choice, and a server-side API as the final fallback. This ensures your app works for everyone, not just those with high-end RTX cards. Managing these failure states is what makes a senior developer's architecture resilient. We've now covered the pipes and the weights, but how does this all handle the messiness of real users? This is exactly what we'll cover in the next chapter. Battle stories, what nobody tells you until your app is live. Look, the biggest lie in browser AI is that it just works once you have the library. In reality, the moment a user sees a 500 MB download progress bar, they leave. From what I've seen in production, user drop-off rates can skyrocket to 70% during that initial model fetch. We are no longer just shipping a 2 MB JavaScript bundle. We are shipping massive binary weights. If you are using Transformers.js or WebLLM, you must realize that the browser's Cache API is your only lifeline. But even that doesn't solve the cold start problem for a first-time visitor. Most developers forget that mobile networks are notoriously unstable. If a single shard of a sharded model file fails with a 404 or a timeout, your entire inference engine will hang indefinitely. You need robust retree logic and partial download support, or your server-side AI killer is just a broken loading spinner. But wait, there is a clever architectural way to hide this massive latency without making the user wait at all. Since we cannot ignore the laws of physics and network speed, we have to change the game. Instead of forcing a user to wait for a 2GB Llama 3 model, we implement what I call the two-tier model strategy. Here is how it works. You immediately load a tiny 50 MB to 100 MB model, something like small m, or a heavily quantized Phi2. This tiny model downloads in seconds and handles the initial interaction, like intent classification or a simple hello. While the user is engaged with this intro model, you pull the heavy-duty weights into background using a service worker or a web worker. The real technical challenge here is the state handoff. You have to transfer the conversation context from the small model to the large one seamlessly once the latter is ready. If handled poorly, the change in logic and intelligence will confuse the user, but if done right, it creates an illusion of instant intelligence. But how do you communicate this complex background process to the user without overwhelming them? To achieve that zero latency feel, your UI must be more communicative than the model itself. First, never rely on standard browser cache. Use IndexedDB via the Cache API to store models so you have granular control over versioning and deletions. Second, you must provide a byte-by-byte progress bar. Users are remarkably patient if they see numbers moving. Downloaded 450 MB of 800 MB is infinitely better than a spinning circle. Third, implement warm-up prompts. This is a senior secret. Run a tiny, invisible dummy task as soon as the model loads. This triggers the GPU shader compilation and memory allocation so that when the user actually sends their first real prompt, the response starts immediately rather than lagging for 3 seconds of compiling. This checklist is the difference between a project that feels like a laggy demo and a professional-grade AI tool. However, even with perfect UX, there is a bigger battle happening regarding data safety and system resources. The real reason many organizations are pivoting to browser AI isn't actually cost, it is compliance. In a recent scenario involving sensitive medical records, we couldn't let a single token touch a remote server due to HIPAA concerns. By using WebGPU and running the LLM entirely on the client side, we created what I call trustless AI architecture. Once the model weights are cached in the browser, the application can literally go offline. We programmatically blocked all outbound fetch requests after the initial load, ensuring that the patient data never left the user's local RAM. This is the ultimate privacy win. You aren't asking the user to trust your privacy policy. You are providing a technical guarantee that the server isn't even part of the conversation. But this privacy-first approach comes with a physical cost that developers often ignore during development on high-end workstations. This is where the battle against hardware begins. Here is the dirty secret of browser AI. Sustained inference is an absolute battery killer. When you push a mobile GPU to 90% utilization for several minutes of continuous chatting, the device will heat up significantly. I have seen mobile devices hit thermal throttling after just 3 or 4 complex prompts, causing the inference speed to drop from 15 tokens per second down to 2. It's not just speed. The OS might start killing your browser tab to save the hardware. As a senior developer, you must monitor navigator device memory and detect if the user is in low power mode before initializing WebGPU. You have to balance the privacy win against the battery loss. If you don't manage the duty cycle of your inference, your app will be remembered not for its AI features, but for being a battery vampire. This is the trade-off we must navigate. Now that we have covered the scars from the field, let's move to the final checklist for actually deploying this to production safely. When people first start with WebLLM or Transformers.js, they often make a fatal mistake. They run the inference loop directly on the main thread. I've seen production apps freeze for 10 seconds just because the model was calculating a single attention head. This kills the user experience and often triggers the page unresponsive browser dialog. In the field, we solve this by strictly offloading all heavy lifting to web workers. You should treat your WebGPU context as a background service. Don't just fetch and run, you need to handle the lifecycle, especially when a user switches tabs or navigates away. If you don't manage the worker properly, you end up with zombie GPU processes that drain the user's battery even after they close your app. You need to implement a clean termination signal and prioritize resource disposal over simple garbage collection. This is the difference between a toy project and a professional-grade browser application. But wait, even if you offload it to a worker, how do you know if it's actually running efficiently on the user's specific hardware? Monitoring local AI isn't like checking your server-side logs. In the world of 2026 browser AI, the server is the user's device, and you have zero direct visibility unless you build it. You need to implement a client-side telemetry system that tracks the reality of the edge. I recommend using tools like the WebGPU inspector during development, but for production, you must track metrics like time to first token and VRAM pressure via the Navigator GPU adapter info. Most developers forget to monitor context loss events. If the OS decides to reclaim GPU memory for a high-end game or a video call, your AI model will crash silently. You need a robust retry and recovery mechanism that can resume from a cached state rather than starting the download from scratch. Real-world reliability comes from assuming the client environment is hostile and unstable. We need a stack that covers everything from hardware capability detection to high-level inference monitoring. This way, you don't just hope it works, you know exactly why it failed. Monitoring tells us there's a leak or a delay, but how do we make the actual experience feel faster for the user? To make local LLMs feel faster than 100 Ms ping to a server, you must implement token streaming. If you wait for the entire generate call to resolve, the user is staring at a spinner for 5 to 10 seconds. In modern frameworks like Transformers.js or LiteRT, we use callback-based stream handlers. As soon as the first token is sampled from the KVV cache, we push it to the UI. This reduces the perceived latency to nearly zero. Look at this code. We are using a streamer object that hooks into the internal loop. This allows the UI to render word by word, creating that typing effect that users have come to expect. However, there is a hidden cost here managing the KV cache memory manually if the sequence gets too long. If you aren't careful with the context window, you'll run out of RAM before the sentence even finishes, leading to a hard crash. This implementation is the standard for 2026. Streaming feels fast, but if the model is 4GB, the wait before the first token is still painful. How do we balance model size without losing the AI's intelligence? Choosing the right quantization level is the most important deployment decision you'll make in 2026. If you ship a 16-bit float model, 90% of your users won't have the VRAM to load it, and your bandwidth bill will skyrocket. If you ship a 2-bit model, the AI will start hallucinating gibberish. The industry sweet spot right now is 4-bit quantization, specifically methods like Q4KM. This gives you a massive reduction in model size, usually around 70%, with only a tiny hit to perplexity or intelligence. In this table, notice how the VRAM requirement drops significantly as we move from F16 to Q4. For a typical 7B parameter model, we're talking about the difference between needing a high-end workstation and running comfortably on a standard consumer laptop. You must test your accuracy-to-weight ratio before every release. Don't just pick the smallest model. Pick the one that fits the average user's device while still solving the problem. That concludes our technical checklist for deployment. But the landscape is shifting daily, so how do we build a solid roadmap for the next 12 months with all these moving parts? We've covered a lot of ground, but the core takeaway is simple. The era of reflexively reaching for a server-side API for every AI task is over. By 2026, as an engineer, your first question should be, can I run this on the client? We've seen how WebGPU and WebLLM allow us to bypass high-latency API calls and massive cloud bills. In the field, I've seen teams cut their inference costs by 90% simply by migrating their summarization and classification tasks to Transformers.js or WebLLM. This isn't just about saving money. It's about a fundamentally better user experience where the UI never hangs waiting for a network response. Your immediate action items involve auditing your current AI features. If you're handling sensitive user data, the privacy gain of local inference is no longer a luxury, it's a requirement. Start by prototyping with small models like Gemma 2B or Phi3 in a WebGPU environment to get a feel for the quantization trade-offs. The codebases we looked at today are your foundation. But wait, while the software stack is maturing, there is a hidden hardware revolution happening right under our feet that changes how we think about browsers entirely. Looking ahead to 2026, the web browser is evolving into a specialized AI OS. We are moving beyond just utilizing the GPU. The upcoming WEN and API will provide a direct bridge to dedicated NPUs or neural processing units found in the latest silicon. This means that in the very near future, the web applications you build will have the same performance profile as native mobile apps. We are entering a phase of hybrid AI, where the browser handles the heavy lifting of real-time interaction, and the cloud is reserved only for massive, billion-parameter multimodal tasks. In the industry, the winners won't be those who have the biggest servers, but those who can orchestrate the most efficient local models. Don't wait for the standard to be perfect before you dive in. The infrastructure is here, the models are shrinking, and the users are ready for faster, more private AI. The roadmap we've built today isn't just a guide, it's your competitive edge in a world where server-side AI is becoming the bottleneck. This is where the theory ends and your implementation begins. I hope you're ready to build the next generation of intelligent web applications that truly respect the user's device. This concludes our journey now. The real work starts in your editor.